Well, we're very happy to have Asher Berlin up from SLAC. He's going to tell us about thermal relics below an MeV.
Yeah, thanks for the invitation. So this is going to be a talk based on thermal relics that are lighter than the MeV scale, with a particular emphasis on thermal dark matter that's lighter than the MeV scale. This is based on a couple papers with Nikita Blinov, who was recently on SLAC for the past year and a half. Okay, so I'll just begin by saying we know a ton about dark matter, but we know obscenely little about its mass. So in principle, it could be as light as something around 10 to the minus 31 GeV, below which point its large wavelength would start to disrupt the stellar kinematics of dwarf galaxies. And in principle, it could be as some composite object as heavy as roughly 10 solar masses, above which point standard microlensing constraints and macho searches would start to put the scenario in tension. But a priori, anything in between here is game, and so usually what's done is to use well-motivated scenarios to guide one's thinking within this vast landscape. So most famously, there's a QCD axion, often motivating masses both EV scale, and canonical vanilla WIMP, often motivating masses around the weak scale. But as most of you probably know, from in the past few years, there's been a little bit of doubt cast on the WIMP, largely due to no results from searches at things like direct detection experiments. So if you're looking for another interesting point in mass space from the point of view of a model, you might find a model that points you here. For every model that points you there, you can find 10 others that point you elsewhere. So if you want a nice generalization of the WIMP paradigm that still organizes your thinking within this vast mass range, one way to do that is just demanding thermal contact. So if the dark matter was ever in thermal contact with the standard model bath in the early universe, the viable mass range is drastically reduced. And this is essentially just a generalization of what a WIMP is. And so zooming in on what people typically talk about in terms of this mass range are masses ranging from an MeV to 100 TeV. Things heavier than 100 TeV are typically overabundant, assuming a standard cosmology, so there's typically too much of them today. And things lighter than an MeV are said to typically be run afoul from considerations of Big Bang nucleosynthesis and the cosmic microwave background. These statements down here are largely driven by measurements of ineffective or indirect measurements of the expansion rate of the universe. So ineffective being the effective number of neutrino species. And I should say, a little independently, recently there's been a lot of kind of like creative experimental theoretical collaboration going on in the dark matter community for the past few years, trying to think of new experimental methods and signals to try to probe particle dark matter, especially below the GeV case and often below the MeV case. So there's been a ton of effort from theorists in trying to look for low energy recoil targets, essentially like generalizations of the standard direct detection methodologies that we've come to know and love. However, I feel like there's not been a compensating effort to think about what are well-motivated cosmologies that even live down at these low masses. So if these experiments happen in the near future, I think it's pretty important for people that think about dark matter from a more theoretical or cosmological point of view to ask, like, what is the low-hanging fruit and what's the most obvious thing that these experiments would even be measuring? This is not going to be a main driver of what I'm going to be talking about. There's at least some motivation to begin thinking about these things. So I'm going to be focusing on thermal dark matter. So for that reason, let me define it. So if you look up thermal dark matter in the dictionary, you find that it's defined to be dark matter that acquired its cosmological abundance through thermal contact with the standard model bath at large temperatures. Obviously not the dictionary, but by large temperatures, I mean temperatures much greater than the dark matter mass. Okay, and so this is what I think people typically mean when they think about thermal dark matter. By thermal contact, I mean some sloppy way of talking about chemical equilibrium and kinetic equilibrium with the standard model bath. A more colloquial way to say this is that thermal dark matter is dark matter that was in full relativistic thermal glory with the standard model bath before freezing out. So something like a canonical WIMP that's fully equilibrated with the standard model, some standard model species in the early universe, and then it turns non-relativistic and freezes out in the standard way. So with that, let me just kind of begin by reviewing some of the standard considerations that people talk about from the point of view of any sub-MeV thermal relic. I'm going to have a particular emphasis on dark matter, but a lot of what I'm going to be saying can be applied to any kind of general thermal relic from the early universe. So as I said, this is often driven from considerations of an effective, or the effective number of neutrino species. And you can think of this as essentially just parameterizing the expansion rate of the early universe. So in the early universe, when radiation was dominating the energy budget, Hubble, or the expansion rate, is just controlling is just controlled by the radiation energy density, and you can just define the radiation energy density to be a piece coming from the photons, at least at MeV temperatures, a piece coming from the photons, as well as another piece with some conventional prefactors, but essentially just defines an effective. So this piece here essentially just tells you how much of the radiation energy density at these times is coming from neutrinos and any other stuff, so any other non-standard things. So you often hear that ineffective is just a number that you measure at the recombination, something like 3. But more generally, you can take a different convention, and this is really just a convention, that ineffective is some non-standard dynamical quantity. So if Hubble is some non-standard function of cosmological time, you can essentially, because ineffective is just parameterizing the radiation energy density, because the radiation energy density is parameterizing Hubble, you can think of ineffective as some non-standard dynamical function of cosmological time or cosmological temperature. So for instance, ineffective at the time of primordial nucleosynthesis might not be exactly the same as ineffective at the time at recombination. In the standard model, ineffective is predicted to be around 3, corresponding to the 3 generations of standard model neutrinos. Not exactly 3, due to the fact that these conventional prefactors here assume that neutrinos perfectly decouple at a couple MeV, which in which fact they don't. So there's a 1 to 2% correction from that, but it's pretty close to 3. And you can imagine any deviations away from the standard model prediction of 3, largely from one of 2 like popular classes of scenarios. So the most obvious way to lead to a deviation in ineffective, usually bumping it up above 3, is just to imagine that there's some additional dark radiation. So this is just something with some non-negligible temperature. It doesn't have to be coupled to us, but it's contributing to, it's gravitationally contributing and modifying the expansion rate of the universe. Or you can imagine that there's something that leads to entropy shuffling, or what I call entropy shuffling, which is, so something doesn't necessarily have to be present to lead to a modification ineffective at later times. Namely, if something heated up the neutrinos compared to photons, or heated up the photons compared to the neutrinos, this will lead to a corresponding increase or decrease in ineffective, because as we'll see, ineffective depends on the relative neutrino to photon temperature ratio. So if you can modify the temperature ratio in any way by shuffling entropy between the 2 sectors, that can lead to a deviation in ineffective as well. So to understand how some generic VSM scenario might lead to a deviation in ineffective, there is a few important temperature scales to keep in mind. So this first one here is a model input, so your theory has to tell you this, but by definition I'm going to be focusing on thermal dark matter, and by definition it had to come into equilibrium with the standard model at some point. So at some point it entered equilibrium with the standard model, and that's something, the temperature at which this happens is something that the model has to tell me. And the rest of these are standard model scales. So there's the temperature at which neutrinos and photons decouple, which is expected to occur at a couple MeV. There's the end of BBN. By that I mean this is when most of the important light nuclei that I care about from the aspect of primordial nucleosynthesis have been locked in. Roughly speaking, this happens at around 50 keV. And then there's a temperature associated with the CMB and recombination near the EV scale. So just to simplify this picture a little bit, let me focus on these 2 scales here. So when did dark matter enter equilibrium with the standard model? When did it equilibrate? And how does this compare to when neutrinos and photons are expected to decouple, which is, in the standard model, expected to happen at around 2 MeV. So let me imagine that I have some light thermal relic, so the mass of this light dark matter particle here is well below the MeV scale. In this case, the standard assumption is to assume that although its mass is well below the MeV scale, it was already well equilibrated with the standard model at temperatures much greater than the MeV scale. So at temperatures well before neutrinos and photons decoupled. At MeV temperatures, there are only few standard model players in the game. There are things like electrons, photons, neutrinos. To simplify the picture and just for concreteness, let me focus on the case that dark matter thermally equilibrates with neutrinos. A lot of what I'm going to be saying can be carried over to the case where something equilibrates with electrons or photons, but there are some additional complications. So let me just focus on the case that it equilibrates with neutrinos. In this case, it's just kind of a standard textbook problem. What happens is, once the dark matter turns non-relativistic, so once the temperature drops below the dark matter mass, it dumps its entropy into the neutrinos and heats up the neutrinos compared to the photons. This leads to an increase in the predicted value of ineffective. So ineffective in this standard scenario is assumed to be 3, the standard model prediction, times some additional factor that depends on G dark matter. This G dark matter here is the number of effective relativistic degrees of freedom in the sub-MeV sector, raised to the 4/3 power. And you can try to remember this 4/3 power, because I'm going to be contrasting it with another similar expression in several slides. So you can try to remember this general form. But the basic statement is, if I have 1 degree of freedom that does this, so just put in 1 here. You get a minimal prediction for the deviation in ineffective at the level of 0.8. So in this scenario, ineffective is predicted to be at least roughly 3.8, and that just begs the question, how is this kind of toy scenario constrained observationally? Which I'll just quickly review.
Sorry, this is the coupling between the dark matter and the center modulus through the neutrinos?
Yes, that's right.
That seems kind of crucial to this.
That is crucial to this prediction.
Yeah.
If I replace this with photons, it would be something below 3. You would have some additional factor in the denominator here that would make this prediction less than 3, and there would be an upper bound on the value of this ineffective. If it was coupling to both photons, electrons, and neutrinos, this would essentially equilibrate with the neutrinos with the photons at many times, and also would lead to an increase in ineffective. So there are various kind of routes you can go.
And as far as higher mass states, most of them are frozen out by these.
Yeah. So here I'm imagining, if there's anything at like the GeV scale, for instance, you can do whatever you want at the GeV scale. You can dump entropy into whatever you want. Everything's in equilibrium, so it doesn't really. Everything's in thermal context. It doesn't really matter. So in this case, I'm only interested in things that are below the MeV scale, because things that's going to shuffle heat or entropy around it. After the neutrinos have decoupled from the photon, that's when you can potentially mess things up in an observational way. Okay, so how is this constrained observationally? So let me just give kind of a quick cartoon picture of what people typically talk about when they talk about the physics of BBN, or primordial nucleosynthesis, so the formation of light nuclei in the universe. So one of the standard abundances to consider is that of helium-4 nuclei. And the standard discussion goes as follows. You say, in the early universe, there are neutrons and protons interconverting through weak-scale processes. These weak-scale processes freeze out at a temperature around an MeV, after which the relative neutron to proton number density ratio, so how many neutrons there are compared to protons, is just dictated by a ratio of Boltzmann factors. So it depends on their mass splitting as well as this freeze-out temperature. If you also account for the fact that before nucleosynthesis really gets going, that roughly a few tens of percents of neutrons decay away, so they have some finite lifetime, so a little bit of them are going to decay away before they get bound into lighter nuclei, you get the estimate of roughly 1/7. Okay? Then it's generally true that most free neutrons at the onset of nucleosynthesis end up bound into helium-4. This is just largely due to the fact that helium-4 has a large binding energy considering how light it is. So its binding energy per mass is pretty large. And you can define what people call the helium-4 mass fraction. That's what this Y sub P is. That's the fraction of mass of all baryons that ends up in helium-4. And just by saying that all neutron pairs end up in helium-4 nuclei, you can do a simple counting argument, and you can just estimate it simply in terms of the neutron to proton ratio at the onset of nucleosynthesis. Using this estimate here, you get an estimate of 1/4, which is consistent with, this is consistent with the inferred primordial abundances from measurements that we can take today. The other abundance that people typically talk about is that of deuterium. Unlike helium-4, deuterium is easily broken up, which leads to the famous deuterium bottleneck, which is simply the statement that although a lot of these binding energies are at the MeV scale, you would have expected nucleosynthesis to happen at the MeV scale. It actually is delayed until temperatures around 100 keV, largely due to the fact that the baryon to photon ratio is so small. Energetically, you just don't favor making deuterium or having deuterium hang around to make heavier things until these colder temperatures are around 100 keV. Once nucleosynthesis really gets going, you make deuterium, now you can make heavier stuff. Even then, deuterium is still burning away at the end of nucleosynthesis, and similar kinds of processes are essentially depleting deuterium. So if you look at what the abundance of deuterium looks like, or what it should predicted to look like, you see that its abundance is essentially just dying. It's falling at the very end of nucleosynthesis until these deuterium burning processes freeze out at temperatures around 50 keV. Okay. So that's the standard discussion for these two most discussed elements. And then you can ask, how do the predictions change if I mess with ineffective? This is just a cartoon plot that I made. Actually, the error bars in each of these elements is actually very, very thin, so don't read into this too much, or don't really care about the axis too much. But it's kind of simple to understand. So take the dotted lines, which correspond to ineffective much greater than 3. So this means a much more rapidly expanding universe. what happens is that neutrons and protons freeze out sooner, so the predicted neutron-proton ratio is increased. And because most neutrons end up in helium-4, if I increase the level of neutrons per proton, this leads to an increase in the helium-4 abundance as well. Similarly, if ineffective is much greater than 3, more rapidly expanding universe at the end of nucleosynthesis, I have less time to burn deuterium away, so these deuterium burning processes freeze out sooner, and the predicted increase of deuterium is higher than it would have been in the standard model case. Okay. So this has led several groups for several years to try to run all these codes and run the Boltzmann equations in a careful way and get a bound on what ineffective should look like at the time of nucleosynthesis. And one of the well-cited range of ineffective at the time of nucleosynthesis that I'm going to show here is that it should be close to 3 with a 1 sigma spread at this level. This is essentially assuming, imagining that you only know about cosmology from the observations of the light nuclei. So this is not taking any cosmology into account about the baryon energy density, or the baryon density, for instance, from the CMB. So this is kind of a BDN only analysis. This is some spread. There's some systematic uncertainty in this number that is not shown here, namely due to the fact when you run these codes, you have to adopt certain nuclear rates. Okay, when running these codes, and which nuclear rates you adopt is up for debate. So there's some systematic spread, but I'll just say I really don't care. I just want to take this as a representative bound and what ineffective should be at the 1 sigma level here, and ask what does it imply for my cosmology. Okay, so the other standard thing to consider other than BBN is that of the CMB. And CMB, one of the dominant ways that it constrains any deviation to ineffective, or how it can measure ineffective, has to do with the physics of silk damping, or what's called diffusion damping. Silk damping named after its discoverer, Joseph Silk, years ago. But this has to do with the physics of high energy photons diffusing out of gravitational wells in the early universe, and as these photons are diffusing out of gravitational wells, they're sloshing around electrons. And as they're sloshing around electrons, they're washing away density perturbations in the CMB power spectrum on length scales smaller than the diffusion length. So the more that these photons can diffuse, the more they can wash away power on small angular scales in the CMB sky. So it's simple to understand this physics. You can just, because I just told you the diffusion length matters, so let's try to estimate the diffusion length as R sub d. You can think of this like a stochastic process, so this should roughly go as the square root of number of scatters times the mean free path of these photons. With a little bit of algebra, you can write this as the square root of the mean free path per Hubble. And then you can simply relate the mean free path to 1 over the free electron number density times the Thomson cross-section, assuming that these photons are dominantly just scattering off free electrons. Of course, this diffusion length is physically not not what you measure on the CMB sky. What you measure is the corresponding angular scale here, and that's just the diffusion length divided by the distance between us and the CMB. So this is the angular distance between us and the surface of blast scattering. And the problem here is that this distance between us and the surface of blast scattering is a priori not independently determined. For instance, it depends on how dark energy evolves between recombination and now. So just observations of the CMB don't tell us exactly what this is, so there's some degeneracy. This is what you measure. So to get around, this is what you're after, and to get around ignorance about this, you can consider another length scale. So another length scale that is well measured is that of the sound horizon. This is essentially dictates the peak of essentially dictates the position of the first big acoustic peak in the CMB. So it roughly goes like 1 over Hubble, some maximal distance, and the corresponding angular scale of the sound horizon is that sound horizon length scale divided by the same distance to the surface of blast scattering, this d sub a. And the important point is that the first peak is extremely well measured. It's well measured to some precision of like 10 minus 4, 10 minus 5. So theta s, the sound horizon, if you want a good fit to the CMB, you want to fit the first acoustic peak. This tells you the angular scale of the sound horizon pretty precisely. So you can consider the ratio of these angular scales. The ignorance about this distance of the CMB drops out, so it's just the ratio of distance scales. Because this diffusion length goes like 1 over square root of Hubble, and the sound horizon length goes like 1 over Hubble, this ratio goes like square root of Hubble. And what this says is that for a fixed value of the position of the first acoustic peak, so for a fixed value of the sound horizon angular scale, larger values of Hubble, or larger values of ineffective, correspond to enhanced diffusion, so bigger diffusion lengths. So what this means is ineffective is much greater than 3, you essentially have increased silk damping, and you wash away more power in the high L, what's called the silk damping tail of the CMB. So that's what you see from the numerical simulations. Actually, quite surprisingly, it wasn't known right away. So when you run these big CMB codes, it's kind of hard to say what is the driving physics. It was actually not really understood. I think until this paper, I could be mistaken, but I think it was this paper that really pointed out clearly the physics of how the CMB is constrained and ineffective. And the actual bound and ineffective at the time of recombination has some systematic uncertainty. Depends on what kind of cosmological data sets I want to combine and put in my analysis. Here's one well-cited range of what ineffective should be at the level of 1 sigma. And once again, I really don't care what the precise number should be. I'm just going to use this as a representative value, and if it, using some other combination of data sets shifts us around a little bit, it won't really change the story I'm trying to say. But let me just adopt this as a representative bound and ineffective at the time of recombination. So just to recap, the physics of BBN, so corresponding to when the universe was at temperatures of an MeV, and physics of the CMB when the universe was at a temperature of the EV scale, is these independent measurements bound and effective to be close to 3, with some 1 sigma spread at this level. And before I told you this minimal scenario of dark matter, some thermal relic coupling to neutrinos led to this minimum deviation here. So this was the minimum deviation, and the statement is this is in conflict with these observations. So this has led people in the dark matter community for many years to make the following claim, that thermal dark matter should not be lighter than the MeV scale. If any thermal relic was lighter than the MeV scale, it would lead into conflicts with either of these 2 independent measurements. So I'm not going to say that this statement is wrong. I'm just going to say that this statement hides some assumptions. There's some implicit assumptions that I think is worthwhile to look into. So I want to talk about a simple loophole, a way out that I'll refer to as delayed equilibration, which should become clear in a few slides, why I'm calling it that. So to talk about this loophole, let me just start by asking a question. How ubiquitous is it that dark matter entered equilibrium with the standard model before neutrinos and photons decoupled? Okay, neutrino-photon decoupling is expected to happen at a couple MeV. How inevitable is it that dark matter equilibrated with the standard model before then, if it is thermal? So let me just show you a slide from a few slides ago, something I already showed you. This is the standard assumption that dark matter thermally equilibrated with neutrinos well before neutrino-photon decoupling, and its mass is well below MeV. And this was the minimum prediction that it's ineffective. If you go through this calculation, you realize that this is actually an important assumption, because you realize that actually this assumption of ordering of scales is actually in one-to-one correspondence with this result. So that's why I'm asking this question. Because this assumption is so tied to this calculation, I want to investigate how natural is it, how inevitable is it that actually this was the ordering of scales. So to do that, let me just remind you of some well-known physics about thermal dark matter. So what's famously known as the Lee-Weinberg bound is simply the observation that if thermal dark matter was solely coupled to us through the electroweak force, through the standard model electroweak force, that in order for it to not be too abundant today, that its mass should be parametrically larger than the weak scale squared over the geometric mean of the temperature at matter radiation equality and the Planck mass. Temperature at matter radiation equality is around 0.8 eV. This geometric mean is roughly 10 to eV, such that this ratio is a GeV. So what this tells you is that to not be overabundant today, for there not to be too much thermal dark matter today, if it exists, and it only couples us through the electroweak force, it should be heavier than the GeV scale. You can say this another way, and say if thermal dark matter is significantly lighter than the GeV scale, this requires is probably too strong of a word, but strongly motivates the presence of new dynamics. For instance, new light mediators that are often comparable in mass to the dark matter itself. Where chi here is the dark matter, and phi is some new force. Okay, so this is the kind of standard Lee-Weinberg discussion. And this.
What is the equilibrium?
So this is the temperature at which the amount of energy density in matter and the amount of energy density in radiation were the same in the early universe. Which, if you run the clock backwards compared to like measurements that we can make and assume standard cosmology, this is expected to happen when the universe was at a temperature of around an eV. 1 eV. So just a little bit below an eV. Yeah. So this is when radiation. This is after the universe cooled past this temperature. That's when you started becoming matter dominated. You could grow structures more easily. And essentially, this encodes how much dark matter there is. So if there was a lot more dark matter than the amount that we measure today, this would have happened sooner. This temperature would have been higher. So essentially, what the temperature of matter radiation quality is an indirect way of telling you how much dark matter there is. Because when the amount of matter overtook radiation, that's essentially a measurement of how much matter there is. Okay, so this is all standard, but it's not a standard to talk about how these new forces affect equilibration. So let's ask how these new light forces affect equilibration. To do that, I'm going to talk about some rates. So these capital gammas are rates for the dark matter to be able to equilibrate with the standard model. Things tend to equilibrate in the relativistic limit, so let me write them in the relativistic limit. And the form of this equilibration rate depends on the process that is happening. So if, for instance, dark matter is equilibrating with the standard model by elastically scattering off of the standard model, this rate will go like temperature. In the case that equilibration is happening through decays and inverse decays of some light mediator that is highly relativistic, that rate will go like 1 over temperature. You can think of it like a time dilation factor. But the important thing you want to do is compare this to the case if dark matter, the rate for dark matter to equilibrate with the standard model, if the mediator was very heavy. So imagine that you have some dimension 5, higher order operator, just some contact operator. As a result, any equilibration rate in the relativistic limit is going to have some extra scale suppression downstairs, and just by dimensional analysis, it has to have some extra temperature dependence. And the important point is, for these things to be relevant, you want to compare them to Hubble. And Hubble during radiation domination is scaling in terms of temperature and temperature squared. So the important point here is that a light mediator is falling or growing compared to Hubble, whereas a heavy mediator is falling more rapidly compared to Hubble as the universe cools. So what you can do is plot gamma per Hubble, so the amount of equilibrating rates that can occur per Hubble time, as a function of a cooling universe to the right. So time, or 1 over temperature, or time is going to the right. And the basic obvious point is that a light mediator, so if I'm above this dashed line, that means I'm equilibrating. If I'm below the dashed lines, that means I'm remaining decoupled. The basic point about light mediator is that it overtakes Hubble until I drop below some characteristic mass scale. Then it goes to a heavy mediator-like limit. But for a heavy mediator, it's just always falling compared to Hubble. So the basic kind of obvious point that this is showing you is that light thermal dark matter, which motivates light mediators, light forces, tells you that it had to enter equilibrium at some point, assuming that I can talk about high enough temperatures. For something like a canonical like TeV WIMP, this would be a very high temperature. But if the dark matter is light, this temperature doesn't have to be so early on in the universe. So I have to be able to talk about high reheat temperatures such that I can imagine the universe as a thermal bath by the time this temperature is occurring. So what I want to investigate, I just showed you that entering equilibrium is natural from the point of view of light mediators. What happens at this point of entering equilibrium, so this point right here, happens after neutrino-photon decoupling. I'll motivate this a little bit more, but let me just ask what happens. Okay, so here's the standard assumption once more. Equilibration happening before neutrino-photon decoupling. Now we just take the non-standard assumption, just flip it. So imagine that some sub-MeV relic equilibrated with neutrinos well after neutrinos and photons decouple from each other. As you're going to see, as a result, we're going to gain some sensitivity to physics in the UV. Something analogous to the amount of UV sensitivity that Friesen dark matter has, if you're familiar with that. If not, that's okay. But what I'm going to tell you is that I'm essentially going to gain some sensitivity to the initial dark matter temperature before it equilibrates. Although the sensitivity will to UV stuff will drop out. I won't be sensitive to it if the initial dark matter temperature is much smaller compared to the standard model temperatures. So I'm imagining that dark matter is part of its own thermal bath before equilibrating, but let me imagine that it's a much colder thermal bath before equilibrating. So that's my assumption.
What do you have something specific in mind for the operator or the interaction that equilibrates dark matter and neutrinos?
Yeah, I do. So actually the last third of this talk probably won't take a third of the time, but the last section will be actually like a specific interaction, like a simplified model, and then a realistic model. And it will usually be the case that it's coming from some new light particle that dominantly couples to neutrinos, some new light force that dominantly couples to neutrinos.
Okay, because it's not so easy. I mean, if you have right-handed neutrinos,
Oh, yeah, that's exactly right.
you have light direct
Yeah,
neutrinos.
it will be
like
like a light sterile neutrino. Yeah, it's something like a Meyer That's,
Right.
if you're familiar with that,
Yeah, yeah.
so that's what I'll be doing.
Okay.
But the first thing I'll do, I'm slowly building up to that.
Mhm.
In fact, before I even get to that, I'll write down just a non-gauge invariant Lagrangian and just work out some rates. And then I'll write down a full, like, realistic and sensible theory.
Okay.
Okay, so let me ask, let's imagine that my dark matter is initially part of a thermal bath that's initially much colder than all the standard model temperatures before it equilibrates. By definition, it's going to be a comparable temperature when it equilibrates, but before it equilibrates, let me imagine that it's much colder. Because in this case, my sensitivity to this specific temperature drops out. So what I'm going to be plotting here is this temperature ratio, C sub I, which is defined to be the temperature of species I. I might be neutrinos or dark matter, but species I normalized by the photon temperature, and as a function of the photon temperature. And note that the photon temperature is dropping as they go to the right here. So the universe is cooling, time is progressing to the right. The dotted line shows you the standard model prediction for C sub nu. So this is the neutrino to photon temperature in the standard model, expected to be 1 when the neutrinos are coupled with photons, and drops below 1 after they decoupled and after electrons turn non-relativistic, because when electrons turn non-relativistic, they heat up the photons compared to neutrinos, and essentially you asymptote this famous textbook approximate answer of 411 to the 1/3, which we just derived from counting degrees of freedom. It's roughly 0.7. Okay, so let me compare this standard model case, the standard model prediction, to the case where neutrinos decouple, but then they have to equilibrate with a cold dark matter center. Okay, if this is the case, that's shown by the solid lines here, with the dotted line still showing you the standard model case, just so you can compare by eye. But what happens is, if the neutrinos are decoupled from the photons, and they have to equilibrate with some dark matter sector, this costs them some heat. Okay, and they can only be cooled compared to the photons if they've already decoupled from the photons. So this initial cooling with respect to the photons can only happen if this equilibration happens after neutrino-photon decoupling, so at temperatures below an MeV roughly. But you're heating up this dark matter sector as they equilibrate, you're cooling down the neutrinos compared to the standard model expectation. Then what happens here, at least when I made this plot, I had a couple mass thresholds in the theory. So this hidden sector, this dark matter sector, has something like a dark matter particle of a certain mass, and a hidden sector force, where that force particle has a certain mass. And once I drop below the mass of each of those respective particles, they turn non-relativistic, they dump entropy back into the neutrinos, and they heat the neutrinos back up. So these little jumps here correspond to essentially entropy going back into neutrinos once I drop below a mass threshold in this hidden sector. And you'll note that there's some irreducible heating. So this is essentially decoupling and things turning non-relativistic and dumping entropy back in, but things tend to pump heat back into the neutrinos. In the standard case, I could have made the standard cosmology where something couples to, not standard cosmology, but in the standard assumption where something couples to neutrinos, I could have made a similar plot. I wouldn't have had an initial cooling. I would have had the final state heating. So the basic point is, in this scenario where I equilibrate after neutrino-photon decoupling, I cool them initially, and this compensates the later heating that's inevitable. And there's an irreducible heating due to the fact that essentially what I'm doing is I'm taking two decoupled gases, maybe like separated by a wall or something, removing the wall and letting them equilibrate, and one gas is much cooler than the other. That's something that leads to an overall irreducible increase in the co-moving entropy. So there's an irreducible heating that has to be there at the end of the day. Okay. So that was the temperature evolution. Let me take you through how an effective is modified. And to write down some semi-analytic answers, I have to first set up some notation. So the notation that I have here is the G star nu, which is the effective relativistic degrees of freedom of neutrinos.
Is there a simple way of understanding the minimum value of that irreducible heating? Does it correspond to some simple limiting case?
This limiting case, it's the limiting case that this is true, that the dark matter sector started at a much cooler temperature. There's a simple expression that you can write down that you can actually derive from conservation of co-moving energy density. And you can get an approximate form for this line, and it's saturated when the dark matter is much colder compared to every other bath of the problem.
But the fraction depends on how many degrees of freedom.
Oh, sorry, and of course, yeah, and more degrees of freedom, and the number of degrees of freedom. Yeah. So if I turn up how many degrees of freedom have to equilibrate, that's obviously going to cost more energy to heat those things up. So if this was made assuming my hidden sector consists of a Majorana fermion and a real scalar, so I think that's an effective relativistic degrees of freedom of 2.75. So this means G star of hidden sector is like 2.75. But if I increase the number of relativistic degrees of freedom in the hidden sector, this would just drop. But as, this would drop, and this would also increase. So initial cooling would become greater. Essentially, the spread of this thing would just increase as I turn up the degrees of freedom. But these effects, for a fixed number of degrees of freedom, this effect is saturated once I make the chi bath much
So
cooler.
the actual, if you wanted the biggest effect of this kind as possible, you'd want as few degrees of freedom in your, it's still, I see, it's kind of, you can sort of think of it as reducing, can you think of it as reducing the amount of an effective that you get per degree of
Yeah,
freedom in the hidden
exactly,
sector?
exactly.
You can kind of think of it that way.
Exactly.
Right? Okay.
Yeah.
Thanks.
And so this is actually just thermodynamics, and I was kind of happy when I found it and we wrote this paper, but I just want to say this is actually not new. I actually found it the other day, or not the other day, but several months ago in a paper by Chaco and Lawrence Hall from like the mid-90s. So they had already, to some degree, thought of this stuff, not from a dark matter viewpoint. They were thinking about it in terms of actually like mirons and stuff. But yeah, so this is, I think it's new to apply this to dark matter particles. But I'll show you the actual expression for ineffective, and you'll see for a fixed amount of degrees of freedom, this is essentially a way to alleviate the deviation to ineffective at the maximum way, if you want to do something that's kind of purely thermodynamical. Okay, so let me take you through the semi-analytic versions, or semi-analytic expressions for what ineffective should look like. So G star nu is the effective relativistic degrees of freedom of neutrinos, 7 A's for Fermi statistics, 3 generations of left-handed neutrinos. I'm going to define this initial condition parameter. This is essentially a boundary condition. This is the dark matter to photon temperature ratio before equilibration. So because it's before equilibration, it's essentially a free knob. At this level in my theory, I'm just going to treat it as a free parameter. But I'm going to imagine mostly be interested in the case where this is much smaller than in which case the sensitivity to this parameter drops out. I'm also you'll see this notation around. TKE is the temperature at which these things equilibrate. KE is standing for kinetic equilibrium. But TKE is the temperature at which dark matter enters equilibrium with the standard model. Okay, so if you go through the calculation of what ineffective looks like, you have to ask what temperature are you talking about. For temperatures well before equilibration, so temperatures well above the equilibration temperature, the deviation ineffective just looks like the standard form for an uncoupled dark radiation bath. Okay, so it depends on how many dark matter relativistic degrees of freedom there are compared to neutrinos. It depends on this temperature ratio before equilibration. This is the standard form for ineffective for something that's just not coupled. You have to know what its temperature is, and this is what this ratio tells you. When you go through the calculation, you ask, okay, what happens when the temperature drops below the equilibration temperature? And this will tend to happen when things are relativistic, so let me ask before things turn non-relativistic. They're still relativistic, but after they equilibrate, what happens? You go through the calculation, this is the form for ineffective that you find, and it actually turns out to be exactly the same, approximately. And this is approximately true because it's approximately true because when relativistic things equilibrate, their co-moving energy density is approximately conserved, and because ineffective is telling you how much energy density there is in chi, this hidden sector bath, and neutrinos, and I'm just shuffling it back and forth between the two sectors, but I'm not changing the total amount. Ineffective is largely unchanged. So there's actually kind of a cute aside, I think, from this point of view, in that let's imagine that chi never goes non-relativistic before the CMB. That can't be for a dark matter story, but let's just imagine now. Forget that chi is dark matter. Let's just say it's some sub-EV sector. This means that I could have, 1 billion degrees of freedom equilibrate with neutrinos after neutrino-photon decoupling, and that would lead to a negligible deviation in effective if this temperature ratio was smaller, was smaller than like 1 billion to the 1/4 power. So if I'm willing to dial down the initial how cold this is, I'm willing to make it very cold, I can have as many degrees of freedom as I want, equilibrate with neutrinos, and essentially depopulate the universe of cosmic neutrinos. And it would lead to no deviation in effective as long as these things are relativistic. Of course, that would be falsifiable or measurable from considerations of if large-scale structure, like galaxy surveys, if they can measure the neutrino mass precisely, that would be a way to differentiate this scenario. Or if you actually detect the cosmic neutrinos, that would be a way to differentiate that scenario. But ineffective, the expansion rate would be Of course, for dark, let's forget that now, but because dark matter has to turn non-relativistic, and when the temperature drops below its mass, you get this little irreducible heating. And you can see, even if I take this initial temperature ratio to be 0, assume this sector is much colder, there's some irreducible deviation in effective, which depends on the relativistic degrees of freedom in dark matter compared to neutrinos. And so this is the important, so this is the limiting form, limiting predictions within effective, assuming that the sector is much colder. And so I can actually just solve the Boltzmann equation and verify this. So these dashed lines are just the approximate solutions I just showed you. The solid line is actually just solving the Boltzmann equation numerically and getting the right answer. This was the case if I had a sector composed of a Majoran, a fermion, and a real scalar, so a few degrees of freedom. This was the same case, but assuming that equilibration, taking the standard assumption that equilibration happens before neutrino-photon. So before, people would say, oh, look how big the deviation in effective is. But if you just relax that assumption, say, let me assume that equilibration happens later, and the temperature is initially much smaller, then there's some irreducible deviation in effective, yes, but it's much smaller than you typically would have. And so here I'm running it in a way that contrasts it with the previous form that I had. So I told you several slides ago, and try to keep this expression in mind. It was G chi here, I forgot the star, but this is the effective relativistic degrees of freedom in dark matter. And this is the same expression, except the 4/3 has been replaced by a 1/3. So instead of a minimum deviation at the level of 0.8, this is a minimum deviation at the level of 0.2 roughly. So the basic statement is that I can easily have several degrees of freedom that do this and that are completely allowed by the data right now. They're completely okay from the physics of BB and CMB, for instance. However, the interesting point is that in the next few years, like a large suite of ground-based CMB telescopes are going to turn on, and because they're ground-based, they can be bigger experiments, too big of things to put in space, and because they're big dishes, they're going to have better angular resolution. And I told you before, if you have better angular resolution, that's sniffing out the physics of how ineffective affects the CMB, because it modifies silk damping on the high L tail. So CMB stage 4, CMB stage 3, or stage 4 ultimate predicted sensitivity is at the deviations at the 1% level, as opposed to our current sensitivity of deviations at the tens of percent level. So the basic statement is that CMB stage 4 will generically test this classic cosmologies. And in fact, even the equivalent classic cosmologies where I do this trick for things not coupling to neutrinos, but things coupling to photons. So there's a minimum deviation in both cases. I did talk about the photon case today. But the basic statement is CMB stage 4 will generically test it. Okay. So just to recap, let me show you some thermal histories. This is the standard thermal history of a WIMP, showing you the co-moving number density as a function of 1 over temperature. I don't have to go through this probably, but relativistic, non-relativistic, and freeze out. That's a WIMP. You can compare this to freeze in, which is something where you assume negligible abundance in the universe and gradually out of equilibrium is leaking energy density into a dark matter sector. Never equilibrates, but slowly accumulates enough energy density to be the dark matter today. What I'm talking about today, what I told you about, is much more akin to the WIMP paradigm. And in fact, is almost identical to the WIMP paradigm, because if I took a WIMP and I said, let's talk about high temperatures to the left here, I would, you would find at some point that this picture would be lying to you, because if you go to high enough temperatures, if you could talk about high enough temperatures in the universe, even for a weak scale WIMP, you would reach a temperature such that there was no reason to believe that the WIMP was able to equilibrate with the standard model, assuming that it has weak scale couplings to the standard model, for instance. But for me, I'm most interested in a light WIMP, a lightish thermal dark matter particle, such that this point of equilibration happens at a temperature that I know the universe existed at. But at temperatures higher than this equilibration temperature, you have to ask a question: was the dark matter sector hotter or was it colder? If it was hotter, this would lead to a greater value of ineffective today if this thing was sub-MeV. If the initial temperature is lower than the standard model, significantly lower, this alleviates a lot of deviations in effective today. So it's not like freezing, so it's just you're equilibrating, relativistic, and then you freeze out in a WIMP-like way. So just demanding that this happens after neutrino-photon decoupling. This point of equilibration happens after neutrino-photon decoupling, because then I can relax a lot of things. Okay. So that's what I'm referring to as delayed equilibration. Just to show you when that might happen from a model building point of view, let me remind you of the WIMP miracle. So if I write the freeze-out cross-section in terms of alpha freeze-out over the dark matter mass squared, the WIMP miracle is simply the observation when I get the right amount of dark matter if the mass is parametrically related to the freeze-out coupling times its geometric mean, where there's a temperature matter radiation equality. And this geometric mean is roughly 10 CeV. That's all standard, but let me supplement this with equilibration. KE standing for kinetic equilibrium here. By definition, the equilibration rate is comparable to Hubble, at the equilibration temperature, and let me just parameterize the equilibration rate and relativistic limit as a equilibration coupling squared times temperature. With this, I can rewrite the first line in the following, different way. I can say that for dark matter to get the right abundance today, that mass should be parametrically related to the ratio of these freeze out to equilibration couplings times this new geometric mean. That depends on the equilibration temperature. So if I want to take advantage of this loophole, it has to be the case that the equilibration temperature has to happen after neutrino-photon decoupling, which is a couple MeV. So if I plug that equilibration temperature into here, I get that thermal dark matter should be significantly lighter than the KeV scale times this ratio of couplings. Of course, there are bounds from considerations of warm dark matter. Let's say for dark matter, not the thermal dark matter, not to free stream too much, that its mass should be significantly lighter than several or tens of KeV. So if I want that to be the case, this estimate tells me that I need a hierarchy between the freeze out and the equilibrating couplings. This is really just kind of obvious. I mean, to equilibrate late, I need small equilibrating couplings. But this tells you kind of more precisely how small do they have to be compared to the naive expectation if they were comparable to the freeze out couplings that you would expect. So this points a few roadmaps for model building, which I'll get to at the end of this discussion. One way to get this hierarchy, so you just want to ask, what's a natural way to get this hierarchy of couplings? One way is what's been called secluded dark matter for many years, which is what I'm going to be talking about. You could also try to resonantly enhance freeze out, but not equilibration. You could try to just add new dynamics to the dark matter sector that are not responsible for equilibration, but are responsible for freeze out, what people call SIMPs these days. But let me just focus on this, because I think it's the simplest one to discuss. Okay, so let me just talk about a few models. To begin, let me discuss a very simplified model. So a model that's not an engaged invariant, but I'm slowly building up to a real model. So let me just write down a Lagrangian where I have some force particle phi coupled to my dark matter fermion chi, which is coupled to my standard model neutrinos nu. And I'm going to assume that this force particle phi is a little bit lighter than the dark matter particle. In that case, freeze out is dominantly going to proceed in the secluded dark matter-like way. This is what people call secluded dark matter. Where I annihilate the pairs of lighter hidden sector stuff, and this hidden sector stuff has some feeble couplings to the standard model. So in this case, chi annihilates the pairs of phi's, freezes out in that matter, and phi's will later decay in the standard model neutrinos. For a KeV dark matter mass, to get the right abundance today, its coupling should be at the level of 10⁻⁵. So that's just the generic WIMP-like estimate if the WIMP was at really the KeV scale. If the phi is not too light, equilibration is going to be dominated by decays and inverse decays of phi in the pairs of standard model neutrinos. This will be suppressed if the phi is very light, but assuming it's not, if I want this equilibration rate from this process to equilibrate the two sectors, essentially overtake Hubble, before the dark matter sector turns non-relativistic. So if I just want it to be a successful equilibration, this tells me a lower bound on this portal coupling between phi and neutrinos has to be greater than roughly 10⁻11 if the force particle and the dark matter are both at the KeV scale. Let me investigate this parameter space where I relate this coupling to this mass in a fixed way, and also relate this coupling to these masses in a fixed way. So that's what this parameter space looks like. For every dark matter mass, I'm fixing lambda chi to get the right amount of abundance. And every dark matter mass and mediator mass, so this is the dark matter to mediator mass ratio, for every point in this plane, I'm fixing lambda nu set to the lower bound necessary to equilibrate successfully. So here you see lambda nu is ranging from 10⁻8 to like 10⁻10 across this plane. And this parameter space is kind of bounded in a simple way. At low masses, if dark matter is too light in this case, it's just ruled out from considerations of warm dark matter. If this mediator is too light, at least in this model, the induced self-scattering rate is too large, and the standard considerations of self-interacting dark matter for merging galaxy clusters, like the bullet cluster, rules that scenario out. And then there's just a hard upper bound on the mass, because if I want to avoid these ineffective constraints, I said that dark matter has to equilibrate relativistically at temperatures below a couple MeV, so that sets a rough upper bound on what the mass of the dark matter should be. Okay. That's the toy model, just to give you some intuition. But now let me jump to a more complete model. So this more complete model will be something like a theory of neutrino masses, so something like a seesaw, like theory of neutrino masses, if you're familiar with that. So here, I have some coupling between
leptons, the Higgs, and the sterile neutrino. This will be my Dirac mass-like term, coupling active and sterile neutrinos. And I have something that looks like a Majorana mass for my sterile neutrinos, except this scalar, sorry, this is not a mass, this is a scalar that's charged under global lepton number. It has lepton number 2. Okay, so this Lagrangian at the onset preserves lepton symmetry if I choose to charge the scalar with a lepton number 2. So I'm going to imagine that the scalar, not going into how, but I'm just going to assume that it gets some VEV F, which spontaneously breaks global lepton symmetry, which leads to a massless goldstone, what's often called the Majorana, this J. However, I'm not getting into specifics here. I'm going to assume that there's some source of soft lepton breaking somewhere in the theory, such that this is actually denoted as something like a pseudo-goldstone. So it has some small mass controlled by some soft lepton number breaking terms. In this case, the rest follows just like a standard seesaw, like model of neutrino masses. The sterile neutrino is controlled. The sterile neutrino mass is controlled by the VEV of the scalar times this Yukawa. The mass for the active neutrinos is the Dirac mass squared over the Majorana mass, where this V is the standard model Higgs VEV. So this is just all the standard seesaw stuff. But now let me supplement this with one extra thing, which is my dark matter sector. So to do that, that's my chi. Let me imagine that there's just some new lepton in the universe, but this lepton is additionally charged under its own Z2. So in this case, I don't want it to mass mix with the sterile or active neutrinos, and this makes it stable. So I'm going to imagine that in that case, this is the only term I can write down, coupling chi to this scalar sigma. And then the most important terms that I care about are the interactions of the naturally the lightest particle, the Majoran, with the other light particles, the neutrinos and the dark matter. And the interaction between the Majoran and neutrinos goes like mass neutrinos over F, the scale F, because the Majoran also couples the dark matter in this way as well, gives mass to the dark matter. The scale gives mass to the dark matter. The Majoran couples like M chi over F as well, where chi is the dark matter particle. Okay. Good. So now let me just take you through the same kinds of physics for equilibration. So just like in the toy model, if the Majoran's not too light, equilibration will be dominated by decays and inverse decays of the Majoran and the standard model neutrinos. Okay, and let me just say for simplicity, for these estimates, I'm going to assume that all these scales are comparable, which they don't have to be, but I'm going to assume that the equilibrating temperature is comparable to the dark matter mass, which is comparable to the Majoran mass. Definitely doesn't have to be the case, we're just doing that to simplify some of the expressions that I already taught. So for equilibration to be efficient, the rate for decays and inverse decays has to be comparable to Hubble at a temperature comparable to the dark matter mass. So this is just the, this decay rate goes like 1 over F squared, suppressed by the neutrino mass squared. And here I'm assuming the Majoran mass is comparable to the dark matter and equating it to Hubble at temperatures comparable to the dark matter mass. This gives me an upper bound really on F in order for equilibration to be successful. And the upper bound on F depends on the neutrino mass, Planck mass, and the mass of the dark matter. Okay. Freeze-out is going to proceed in a similar way as well compared to the toy model, but now the dark matter lepton chi is annihilating the pairs of Majorans. And the Wemp estimate is this cross-section goes like 1 over F to the 4th. Okay, and the Wemp estimate is just equating that cross-section to 1 over the temperature of matter radiation equality times the Planck mass. This gives me a different estimate on F. And this estimate of F tells me not for equilibration to be successful, but if it equilibrates, does this freeze-out process lead to the right amount of dark matter to matter? Okay. Where once again, this is the temperature of matter radiation equality. So now if I equate these two conditions on F and solve for the mass of dark matter, I get somewhat of a rigid condition on the dark matter mass. So for this to be a successful thermal theory of dark matter, period, its mass has to be related to the Planck mass, temperature of matter radiation equality, and neutrino mass, which are all standard model scales to some degree, if you consider neutrinos the standard model, or neutrino mass as the standard model. So let's just quickly do this estimate. Total Planck mass, 10 to the 19 GeV. This is an EV, so that's 10 to the 28. 10 to the 28 to the 1/4 is 10 to the 7, so this larger prefactor is 10 to the 7. Characteristic scale for neutrino masses is a tenth of an EV, so 10 to the minus 10 GeV. So 10 to the 7 times 10 to the minus 10 GeV, 10 to the minus 3 MeV, or 10 to the minus 3 GeV, which is an MeV. So this is one of the only reasons I like this model, because it completely independently points to the MeV scale in like a completely accidental way compared to everything else that I was saying before. And it's just a coincidence between Planck mass, temperature and matter radiation quality, which is telling you how much dark matter there is, and the neutrino mass. In fact, had I been a little bit more honest about the hierarchies of these things, this would have turned into an inequality down there. So these models only work if the dark matter is below the MeV scale. And this is just kind of interesting, I think, because before I told you that, a simple way to alleviate the standard constraints for sub-MeV sectors is by coupling the neutrinos.
So the neutrino mass is coming in because the neutrino mass is proportional to the Myron power coupling.
That's right. That's right.
How it's coming in.
That's right. Yeah, so if the mass is too small, this interaction is too small.
So the F scale is what? In this model? I can see it up there.
You mean like numerically?
Yeah, what's the number?
It's like around the GE scale. Yeah. So yeah, pretty light, but that's just because it essentially needs to compensate for the tiny neutrino mass.
So you have very weak couplings, right?
Mhm.
So not that you may not care, but did you just ask the question of how fine-tuned or natural or unnatural this model is to radiative corrections? It might be
It's
okay
very
because of the
unnatural.
weak coupling.
No.
Even despite all these very weak couplings?
Well, it has not that weak a couplings like internally. So amongst hidden sector stuff, it's not so weakly coupled. Between the standard model and the hidden sector is pretty weakly coupled, but amongst hidden sector things, it's not super weakly coupled. So it's actually pretty unnatural.
So you could, if you cared enough, you could try to make some model where there's some approximate Suzy in that hidden
Right.
sector or something.
Or maybe I could try to argue via anthropics that the scale has to be very light, because if it was very high, then the dark matter would never thermalize. I didn't really think about that too much, but yeah. But it is definitely unnatural. That's definitely true.
Sorry, just to understand, what coupling needs to be sort of not small then? What internal coupling needs to be really small, not small?
Well, generically, the coupling between sterile neutrinos and these scalars is not super tiny. Because I'm assuming the sterile neutrinos have order 1 couplings, like their masses are comparable to the scale F. So in that sense, their couplings to other scalar particles are not tiny in the hidden sector. And I could have maybe chosen the sterile neutrinos to be light to suppress those couplings.
I just thought that all the couplings, generically, if you want to freeze out a very light particle, you need very small couplings, right?
Yeah.
But
That's right.
because the masses of things, you want the masses of other things to be, okay.
I don't want other junk to be light. So for instance, take the sterile neutrinos, I don't want them to be light.
You couldn't do something like take F larger and coupling smaller or something like that? I don't know, I can't see my way through it.
I don't think so.
It's fixed, and rounded problem trees.
What fixes F?
B, equation B, the end of B.
Well, I see that, I see the equation for F, but I guess let's see, it's the freeze out. I don't know, I just know that, right, if you have a very light particle, you need very weak couplings to get the right thermal abundance. So,
That's right.
and I just didn't see anywhere where you needed something.
Right, like
I couldn't quite see where you needed something.
the size of this coupling had to be like 10 minus 5 or something
Right,
like that.
exactly.
I don't think that's small enough, though.
So that's a good way to say it. In this toy model, right, this toy model doesn't look like the mass of phi could be pretty light in this toy model, right? So if it went
That's right.
like, in units of TeV, if it went like the coupling squared, you did 10 to the minus 10, TeV may still not even be light enough. Right?
Yeah,
But it would be not, it wouldn't be ridiculous.
that's right. That's right.
So that's, I guess that's kind of what I was thinking.
Okay, sure. But yeah, the thing is, phi in this case, well, let's go back to the model. Here, this scalar has, I'm assuming that this Yukawa's order 1 to make these stereo neutrinos large. So the scalar has like order 1 couplings to hidden sector fermions. So that would, I guess, I would say that is potentially the most dangerous from a radiative point of view. I'm saying that I want order 1
Do you
couplings.
want that scalar to be in equilibrium with those guys? or-
Well, I don't want the stereo neutrinos to be too light because I want to avoid, well, I guess I could dial it down maybe like an order of magnitude or something as well. But there's actually certain aspects of a lot of other details of the model that I haven't gotten into, which is if the stereo neutrinos are too light, they spoil this whole equilibrium story. So I want to make them kind of as heavy as possible to decouple them from the equilibration story. So it turns out if they're light, they can be involved like in a decay to like a stereo neutrino can decay to a myron and an active neutrino. And that decay rate is parametrically larger than the decay rate of a myron in the pairs of standard model neutrinos. And if the stereo neutrino is too light, it can potentially overtake these other things and equilibrate too soon. So,
Okay.
yeah.
I don't want to stop you, I just wanted to.
No, it's okay. I mean, I actually think, I'm just going to mention one last thing and then I'll be done. So there are, of course, for those who aren't familiar, myrons get radiative couplings to charged fermions, so charged stuff. When you work through the usual analysis, this looks like something, it couples via mass, so it looks like something had mixed with a Higgs with a mixing angle the size of 10 to the minus 15, roughly. So the basic point I'm just showing here is that, other couplings can be relevant, but they're generically kind of like super suppressed. Maybe there would be interesting bounds if this myron was very light, like sub-MeV, but I'm generally interested in the case where it's comparable to a K. So there are a bunch of other constraints. There's things like stellar cooling, supernova cooling, inducing neutrino scattering in the early universe, inducing dark matter neutrino scattering in the early universe, direct searches for myron stereo neutrinos, and these are kind of systematically step through all the things in the paper. And these things typically aren't relevant. By far, the relevant thing is future CMB measurements. So better angular, more CMB measurements that have more angular precision are essentially going to generically test these kinds of cosmologies, independent of what the model is. So let me just end with a takeaway. So I talked, some of these don't really show up, but I talked about something analogous to a WIMP paradigm, where it's very analogous to a WIMP if you just talk about WIMP at high enough temperatures, and it started out cooler. So I would argue that something like this is very plausible for something like a WIMP if you had very high reheat. This happening late, which allows you to avoid these bounds and ineffective, is motivated from the physics of light mediators. I discussed a little bit, like I motivated these masses at the very beginning from the point of view of direct detection. And that was actually my original motivation. So far, I've found related scenarios for these kinds of models, but only so far contrived scenarios that can lead to detectable, for instance, nucleon scattering rates at these proposed low threshold direct detection experiments that people have thought about or so. So nothing really natural. Really, the thing that will do the best job is, as I said, future CMB measurements, and to some degree, better measurements of warm dark matter. So there are things equivalent. There's something like a 21 centimeter forest instead of the London alpha forest that will place better bounds on warm dark matter, which will be sensitive to these, in between KeV and MeV dark matter masses. Future work. So I mentioned briefly that there's an electromagnetically coupled version of the story. So the story from an ineffective point of view is nearly identical. You can alleviate the standard bounds of ineffective by coupling to electromagnetism instead of neutrinos. You like that more? But typically those models are run, there's a lot more things to consider because stellar cooling bounds from things coupling to electromagnetism are usually a much bigger deal than things coupling only to neutrinos from the point of view of stellar cooling. Something I'm about to finish now, I think, which is kind of cool, is in these models, if you equilibrate during nucleosynthesis, so in between a KeV and an MeV, ineffective is not just a number during nucleosynthesis. It's not like ineffective is 4, ineffective is 2. Actually, if you plot its effect on Hubble, ineffective is essentially some dynamical function of temperature. or dynamical function of time. And you can't just recast the previously existing PDN bounds. And those haven't been worked out before, so that's some work that I'm about to finish right now. So it turns out you can have drastic modifications to the expansion rate of the universe if they happen during certain epochs of PDN. Along the same lines, I think just more generally, I think these direct detection experiments, the ones that people have talked about, what might be the future of dark matter in the dark matter community in a little bit, there really hasn't been a lot of thinking from what are well-motivated cosmologies. This is one thing I talked about, but they have one example of a model that they mostly talk about, which is MeV scale freeze-in for things coupled to ultralight dark photons. That's the prime model that people talk about, but I don't think it's really properly understood at this point. What kind of cosmologies would such experiments generically be testing? So I think more generally that's an interesting thing to ask. And that's it. Thanks.
Do we have any other questions for Asher?
When is the 21 centimeter measurements coming in?
Sorry, the what?
The 21 centimeter measurements.
Oh, that, I'm not so sure.
Well,
Nothing is up and running yet. So things have to be up and running, which I'm not sure when that's going to happen, but people speak about it like it's in the next few years. And then the sensitivity that they ultimately talk about for their projections are assuming a bunch of other astrophysical and cosmological measurements all converging, and some other parameters very precisely. So it's hard to say if those things will happen in the near future. But from just from a 21 centimeter point of view, 5 years, less than 10 years. That's what you talk about.
If there are no further questions, let's thank Asher again.